Hello friends, welcome to engineering tutorial. Now in my previous video I discussed about the full wave rectifier of center tap type or the center tapped full wave rectifier. So we discussed about the circuit diagram of the full wave rectifier, uh, the circuit behavior during the positive and negative half cycles, and the disadvantage of the center tap type full wave rectifier. The disadvantage which we identified was that it was very difficult to locate the center tap point in the center tap full wave rectifier in the secondary winding. Sorry. So for that reason, uh, an improved version of the full wave rectifier was come up with. It was designed in order to overcome the demerit or the disadvantage of identifying the center tap point. So that improved version of full wave rectifier is the bridge type full wave rectifier, which we will discuss now. So let's get started. Why the bridge type full wave rectifier? So there are two reasons why the bridge type full wave rectifier is generally used in place of the center tap full wave rectifier. As I said in my previous video, the center tapped full wave rectifier has one disadvantage, one major disadvantage, which is that it was very difficult to locate the exact center tap point. Exact point means middle point in the secondary winding across which the load resistance is connected. Okay, so this is the center tap full wave rectifier. The location of this middle point O is very difficult. Okay, for that reason the center tap rectifier is very rarely used these days. The bridge type full wave rectifier is more commonly used. The second reason or the second demerit of the bridge type full wave rectifier is that the output the second disadvantage of the center tap full wave rectifier is that the output of the center tap rectifier is low, because during a half cycle, any positive or negative, the diode uses only half of the secondary winding voltage. The full voltage is not utilized. Okay, marked by these points, the maximum voltage which occurs across the secondary winding, which is split into two parts because of this center tap point. So during any half cycle, positive or negative, only this much portion of the voltage which appears across the secondary winding, which is split into two parts, is used. The entire voltage is not used. So that is another disadvantage of the center tap rectifier. Because of this center tap point, the voltage which appears across the entire secondary winding, which is transferred, which is stepped down from the primary to secondary winding, is split into two parts. During any half cycle, only one of the diodes is on, so only this much of voltage which is involved in the particular loop, closed loop, only that much of voltage is utilized. The entire secondary winding voltage is not used. Okay, so that is another disadvantage of the center tap full wave rectifier. So in order to overcome these two disadvantages, the bridge type full wave rectifier is used. Okay, so let us see how the circuit of the bridge type full wave rectifier looks like. Okay, so this is the circuit of the bridge type full wave rectifier. Why it is called as bridge type full wave rectifier? Because of this design, this arrangement of diodes. As you can see, there are 4 diodes which are used, which are connected in this way to form like a bridge. Okay, a bridge circuit. Okay, so the usual components are used. First we have is the AC supply, the 230 volt 50 hertz AC supply. Then we have a step down transformer sorry, which converts the 230 volt into a lower voltage level, generally it is 12 volt AC. Then we have this 4 diodes which are arranged in the form of a bridge, and a load resistance is connected across which the output is obtained. Okay, so you are clear about this circuit diagram. Now, the circuit operation or the behavior of the circuit during positive and negative half cycle. Now, I have already discussed about the positive and negative half cycles in my previous videos related to diodes. So, please check out those videos before you go into this, so that you understand this in a better way. Now, we all know that the AC waveform has two half cycles, the positive half cycle and the negative half cycle. So, during this positive half cycle, during the positive half cycle, the top end of the secondary winding, which is A, it becomes positive, and the bottom end of the secondary winding, that is B, becomes negative. Okay, A is positive, B is negative. Now, if you look closely at this circuit arrangement, the positive end, A is positive, it is connected to the P type end. Okay, this is the P type end. You are already clear about the P type and N type ends of the diodes. I have already mentioned that in the introductory part, the basic introduction part to diodes. So, please check out that video also. This positive end is connected to the P type end of D1, and the negative end B, which is negative, is connected to the N type end of D3. So, this all happens during the positive half cycles, when A is positive, B is negative. The positive end is connected to P of D1, the negative end is connected to N of D3. So, in this circuit arrangement, D1 is forward biased and D1 and D3, they are forward biased. Okay, in this arrangement, D1 and D3 are forward biased because positive end is connected to P of D1, negative end is connected to N of D3, like ends. Okay, but in the same arrangement, the positive end is connected to N of D4 and the negative end is connected to P of D2, opposite connections. Positive is connected to N, negative is connected to P of D4 and D2 respectively. So, these two diodes, these two crisscross opposite diodes D2 and D4 are reverse biased and open circuited, and D1 and D3, these two opposite crisscross pair of diodes are forward biased and behave as a short circuit. So, you are clear, during the positive half cycle, A becomes positive, B becomes negative. The positive A is connected to P type end of D1, the negative B is connected to N type end of D3. Because of this, D1 and D3 are forward biased and behave as a short circuit. But the same positive A is connected to N type end of D4 and the negative B is connected to P type end of D2. So, because of this, D2 and D4 are reverse biased and are open circuited. So, the circuit behaves in this way. As D1 and D3 are forward biased, they behave as short circuited, okay, and D2 and D4 are reverse biased and so they are open circuited. No current flows through them. We all know that current always flows from a higher to a lower potential, that is from positive to negative end. So, the current, the direction of flow of current, as you can see, is marked by the black arrowheads. Okay, this denotes the direction of flow of current. It flows from A, the positive end, takes this path through the short circuited diode D1, then takes this path through point C and travels through the load resistance. Okay, please pay attention to the direction of flow of current through the load resistance. It travels from C to D from left to right, okay, from left to right, from C to D. Then again flows through the short circuited diode D3 and it reaches the end point at B, which is the negative end, from positive to negative through this path denoted by the black arrowhead. Now, the important thing to take care of or to pay attention to here is the direction of flow of current through the load resistance. It is from C to D and the output voltage is taken across the load resistance as V output. Okay, it travels from left to right through the load resistance from C to D. During the negative half cycle also it will travel in the same direction. Only then we can call this output as DC and we can get a rectified output. So always pay attention that the flow of current, the direction of flow of current through the load resistance in any type of rectifier should always stay the same. Only then we can call it DC. If the direction is changing, it will become AC. Now, during the negative half cycle, as you can see, the top end it becomes negative and the bottom end it becomes positive. The polarities are interchanged. A becomes negative, B becomes positive. Now, A, which is negative, is connected to the N-type end of D4. B, which is positive, is connected to P-type end of D2. Like ends, positive connected to P and negative connected to N. So, D2 and D4, these two crisscross opposite pair of diodes, they are forward biased and are short circuited. But this negative A is connected to P-type end of D1 and this positive B is connected to N-type end of D3. So, these two opposite pair of diodes D1 and D3 are reverse biased and are open circuited, just the opposite of the positive half cycle. It is just the opposite of the positive half cycle. So, the circuit behavior during the negative half cycle is in this way. D2 and D4 are forward biased, so they behave as short circuit. D1 and D3 are reverse biased, so they behave as open circuit. Current always flows from a higher to a lower potential, so it will flow from positive end from B to A. Now, please pay attention, in the positive half cycle A was positive and B was negative, so current was flowing from A to B, from positive to negative. But in the negative half cycle, B is positive and A is negative, so current is flowing from B to A. So, the direction of flow of current is marked by the black arrowheads. So, it starts from B, flows through the short circuited diode D2, then flows through the load resistance. Again, pay attention here, the direction of flow of current is again from C to D, from left to right through the load resistance. So, in both the cases, during the positive half cycle, the direction of flow of current is from C to D, from left to right, from left to right. Also during the negative half cycle, the direction of flow of current through load resistance is from C to D, from left to right. So, in both the positive and negative half cycles, the direction of flow of current through the load resistance stays the same. That is very important, because only when this happens, we can call the output voltage across the load resistance as DC. If the current would have flown from D to C, okay, just imagine if the current would have flown from D to C, we would have called it as AC signal, because the polarities are getting interchanged alternatingly. But here, during the positive and negative half cycle, the direction of flow of current through the load resistance is remaining the same from C to D, from left to right. So, this output voltage is DC. So, we have successfully converted the AC input into a DC output. So, it follows this path from D through the short circuited diode D4 and reaches A, positive to negative. So, this is the circuit behavior during the negative half cycle. Now, the input and output waveforms and the frequencies. It is the same as that for the center tapped full wave rectifier. The input and output waveforms are the same. The AC waveform has two half cycles, positive and negative, and as it is a full wave rectifier, so we will have outputs during both the half cycles. Here it is a pulsating DC output. So, it is in the same direction, there is no negative half cycle because it is DC. Okay. So, there is output during both the half cycles, that is during positive half cycles and also during negative half cycle, and it is all in the same direction, and it is pulsating DC. It is not pure DC. It is then passed, this signal, this pulsating DC output is then passed through a smoothing capacitor, which is an electrolytic capacitor with a high discharging time constant, to convert it into a almost smooth DC or flat line DC. It will not be completely flat line, almost smooth, almost flat line. Okay. Now, the input and output frequency, it was also the same as I discussed in center tapped full wave rectifier. From here to here, okay, for the AC input waveform, from 0 degree to 360 degree or from 0 to 2 pi, it constitutes one cycle, one complete cycle of the AC input. But for the full wave rectifier output, this from 0 to 180 degree or from 0 to pi, this will be one cycle of the pulsating DC output. So, for one complete cycle of the input AC, we get two complete cycles of the pulsating DC. So, the output frequency is twice that of the input frequency. It is the same as that in the center tapped full wave rectifier, because no matter what the subcategory is, it is still a full wave rectifier. So, the principles will remain the same, just the difference is in the circuit arrangement. This is the center tapped full wave rectifier and this is the bridge rectifier, but the principles, all the other parameters will always remain the same because it is a full wave rectifier. Now, the efficiency of the full wave rectifier, as I said, the parameters will always stay the same. So, the efficiency here also is same as that for the center tapped full wave rectifier. So, the efficiency of the rectifier is the DC output power divided by the AC input power. So, this is the expression, final expression. Now, there is a long process of deriving this whole thing by calculating the RMS value and the average value. We will discuss that in a separate video because it is very long to accommodate in this video. So, here it is given by the efficiency is 0.812 by 1 plus RF by RL, where this small r subscript small f is the forward resistance of the diode and RL is the load resistance. The forward resistance, as I have already discussed in the basic introduction part, is the ratio between change in forward voltage to the change in forward current across a diode, and this is calculated as 81.2%. Now, this ratio RF by RL is very small as compared to 1, so it is often ignored, it is negligible, and we get almost 81.2%, okay, as the efficiency. So, here we have discussed about the concept of full wave rectification through bridge type full wave rectifier. So, we have discussed why the bridge type full wave rectifier is used by identifying the disadvantages of the center tapped full wave rectifier. We discussed about the circuit diagram, the circuit arrangement, why it is called a bridge type rectifier, because of the special arrangement of diodes which look like a bridge of sort, and we have discussed the circuit behavior during the positive and the negative half cycle. Also, we have discussed about the input and output waveforms and the frequencies and the efficiency of the full wave bridge type rectifier. So, I hope you like this video. Now, in my next video, I will be discussing about the derivation part for the efficiency of half wave and full wave rectifier, and also the various other applications of diodes such as clippers, clampers, doublers, multipliers, and all of that. So please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.